Good afternoon, everyone. Welcome to my presentation. Today, my topic is towards US-based real-time video streaming and data analytics for estimating highway traffic flow characteristics. This research is a collaborative one between the Department of Civil and Environmental Engineering and the Research Center CADE at Rutgers University, and the Department of Civil and Environmental Engineering at New Jersey Institute of Technology. We know that a stable and consistent flow is generally considered a safe traffic condition. People use 3 traffic flow characteristics: speed, density, and flow to quantify the status of traffic flow. Fundamental diagrams can be used to visualize these quantities and their relationship. In this era of sensing technology and artificial intelligence, active research exploring remote monitoring of traffic flow so that staff in an agency like NJDOT can check and receive alerts about the traffic flow without visiting the site. In most works, computer vision-based sensing technology is developed for remote traffic flow characteristics estimation, especially speed. Instead of a comprehensive literature review, which would take a long paragraph to explain, here we highlight the major motivation between and behind the categories of specific applied technologies. The existing systems, including hardware and software, are primarily articulated based on data collection scenarios, like leaving a long distance between the drone and the data collection scene, medium distance, and low distance. Intuitively, based on the distance between the traffic and the camera, and depending on the scenario, suitable assumptions can be made, such as the dimension of a reference object we can use to estimate the distance for speed estimation. For example, the width of lanes, the dimension of a road section, or a license plate if we use a dash camera to record a video. For highways, where we need a mobile video recording platform like a drone, the concepts in existing works we tried do not give us a readily available solution in real-world scenarios. The first major gap we identified is that existing hardware options only give us limited live streaming capability because they lose a significant amount and arbitrary amount of video frames in the air. This makes all the data analytics or software concepts appealing, but impossible to estimate the speed of a vehicle. It makes sense because speed is estimated by the change of location across video frames and the time interval over those frames. For the software, there are 2 categories of approaches, depending on whether you want to estimate the scaling factor between image pixels and real dimensions by the camera settings or the dimension of a reference object. The camera calibration-based approach is not feasible for a US platform because it requires fixing the camera settings like focal length, which can only handle vehicles at a certain distance from the camera. The reference object-based approach is more feasible, but somehow less validated. We'll have to articulate, implement, and evaluate a promising method, especially regarding accuracy and computational time.
So here we would like to show in a more detail how our idea come up with by exploring the most related works regarding the hardware system. Those 3 examples we identified is like this. So you can see in the first example, the US would transmit the video to a local computer through on-premises network, meaning that you basically use your own, you have to configure the network by yourself instead of using existing service. And this actually applies to all the related works that we identify, meaning that that's where your frame starts to get lost, because as long as it leaves the US and then it would suffer from possible loss when it gets into a controller or a local computer. Those controllers are similar cases that you see with the manufacturer's setting. For example, you have controller attached to the US. No matter of whether you have cable or other network on the following steps, as long as you have the first step coming with the frame loss, then it's impossible to recover the data or understand how many arbitrary frames are lost. So a simple setting for the example 3 is plotted here. So to get rid of all the on-premises network in the system, our idea is really simple, just to make a direct connection between the UAS and a computer so that you don't lose any frames. However, since we have to connect them, meaning that your computer cannot be remote, so it has to be on board, which is like mounted on the drone. So we need an onboard computer, which means very specialized and compact computer that can be mounted. And then we use a cloud service because this step has to be remote. So this way we can ensure minimum or even no frame loss because of the commercial cloud service, which provides a secured practice. So after that motivation, we still have pretty complex overall hardware system as shown here. On the left side, we have the drone mounted with a computer. And then we'll have to transmit the data to the internet. However, the onboard computer usually has the ability to the network access capability. However, it's limited. So we have to introduce a powerful router so that can get you the data on the cellular internet via 5G. We pick up 5G because the capacity of a router still constrains the uploading volume of your data. So we just want to leave no constraints on this step. So we just have a large one, which is sufficient based on our calculation of the expected data volume. Meanwhile, another good thing about the router is that it can enable us to connect the onboard computer with a remote but local monitoring computer, which means that the operator can use the computer which is on site but right near the UAS to watch the operation happening on the onboard computer and the drone. And finally, the remote user can access a cloud server in a typical way to see the videos and analytics. From the software perspective, we have a pretty long pipeline from data retrieval to the final product. So here we just highlight some of those key points. So first we need to retrieve the data from the drone via its SDK, which is a little unique in our case. And the second major step is to localize the vehicle from detection algorithm. You probably already know the typical one can call YOLO, and video and vehicle tracking methods like deep sort. But here we just want to highlight dataset preparation, because when we apply those most cutting edge algorithms there, we realize that the dataset quality is really the part that bears the most risk of constraining our performance. And for the last major step estimate, which is speed estimation, we highlight how to undistort the geometry within the image and making it able to estimate the speed by scaling up after using the reference object of lane markups. As highlighted before, the proper training dataset collection turns out to be an important tip. In the middle row, you will see our testing dataset would look like this. However, if you go with an arbitrary or typical training dataset, which may look like the one on the left side, which is also used in existing works, it has an advantage of the highest volume that you can find. So I guess that's why people would like to use it. However, if you compare them, they look pretty different. And this is really why people call it dissimilarly distributed training data set, if you go with some of the examples. To solve this one, our testing shows that selecting a similarly distributed data set like the one on the third column, which would give you a much better result. And it also has a good volume. After selecting the proper data set, another tip that we want to highlight is to minimize the types of target objects. When some of the existing works use more object types like car and truck, in those cases, I understand because they want to use the objects, the car as the reference object, so that you can use the dimension of a car to scale up the distance measure. However, it comes with a trade-off that when you do not have sufficient number of testing cases, for example, truck, which is relatively rare in a collected video, then you probably have a precision and recall, which is around 80%. However, if you combine the object classes, then it will give you one category, but a much higher performance, which is around 95%. This aligns with YOLO's recommendation, which is the object detector, that you should have at least certain amounts of training cases and should have a balanced testing training data set. Here we show the qualitative improvement of our tips, aligning with the previous arguments that when you have less number of cases for truck, in this case, then you probably would not be able to identify truck properly. But the modified, like after minimizing the object classes, then you can do it by recognizing it as a vehicle. Another case is that for objects that look similar to truck, which is not, would probably also generate a false positive if you go with the two-class approach. But it is properly rejected in the improved one. So here we show image rectification, that the goal is really to make all the parallels in the real world would also shown as parallel lines on an image, which is not the case if you have a distorted one. So the idea is really to reconstruct that planar coordinate system by identifying the two vanishing points pointing to two orthogonal directions. So then, with the identified location in pixel and distance in image, as well as the reference object's dimension, which is the markup's actual length, we can scale up the identified distance on image to the real dimension. And the time interval between frames is represented as the number of frames per second. As the interface, we have a web application to show a remote user how the original and processed video will look like. And you can put a customized data analytics result on it as well. Since we're working towards real time, we're not there yet. So an ongoing task is to identify the latency through a thorough analysis. We want to identify among the major steps all the computational or transmission time spent across those steps. So we understand which part would probably make the current system not possible for real time in a short run. For example, right now we are very curious about this part because the 5G cellular internet uploading speed provided by those carriers are not too large. So if that's the case, it's really beyond our control that we'll claim that that's really a performance of existing infrastructure. Our approach, since we're using, for example, the markup length as the reference object, it makes it possible to generalized to other traffic flow characteristics, even though most of existing works focusing on speed estimation. For example, we can estimate the number of vehicles per kilometers, since we can measure the distance along the lanes, and we can also estimate the flow, which is number of vehicles per hour, by putting arbitrary or imaginary line as the reference point. So given New Jersey specific application, which is hard-shoulder running strategy, we can show the intermediate quantities are also being applicable to automate applications like this. For example, if you know we're trying to use the signal to turn the temporary shoulder into an active lane or just a shoulder. So if you look at it, it's really that we can do by automating the process of identifying vehicle, whether that's on the shoulder, and shoulder segmentation, and also the speed estimation, whether it's static or moving, to tell whether the approach can be automated. And then you just need a signaling rules design to utilize all the data analytics results. So we also propose a signaling rules to show how a possible approach can be realized by determining the switch of signal based on the 3 results of the data analytics, while vehicle's presence and the segment of shoulder is combined into 1. So you only have 2 columns. I understand that we also need to consider other aspects to make the system more complex and applicable, for example, the pedestrian. And this is the last step, which loops back to the theme of today's presentation track, that is safety. So I want to acknowledge all the partners and sponsors of this project. If you have any questions, please feel free to write to me. Thank you.
All right. Thank you, Dr. Liu, for taking the time to share your research with us. In the interest of time, I think we're going to go ahead and go to our next presentation. If you do have any questions for Mayan, do feel free to reach out, I think, afterwards, and we'll make sure that her contact information is shared with you. So our next presentation is going to be on enhancing vulnerable road user safety in urban streets using LiDAR and crossing warning systems, from Dr. Bronislav Dimitrichevich at the New Jersey Institute of Technology. And we're going to have 2 presentations this afternoon from Bronislav, as some of our colleagues from NJDOT were not able to make it this afternoon. But let me introduce Dr. Dimitrichevich's background. He is an assistant professor at the Department of Civil and Environmental Engineering at the New Jersey Institute of Technology. He specializes in transportation systems analysis, transportation planning, traffic management and operations, and intelligent transportation systems. Recently, Dr. Dimitrichevich has led several ITS research projects for NJDOT's ITS Resource Center, which is hosted at NJIT, including projects focusing on ITS applications in traffic monitoring and control, road weather management, and the application of crowdsourced and CV data in transportation systems and safety analysis. So with that, I'll turn it over to you.
Okay, it's working now. All right, well, thank you for staying this afternoon with us. And in fact, I am jumping in for both presentations. I wasn't supposed to present any of this, but actually my colleagues were not able to attend, so I'll cover for them. Fortunately, I was involved in these 2 projects, so I do have some knowledge of what happened and what I'm talking about. So before I start, I just want to recognize my colleagues who were part of this project, Dr. Lee and Dr. Beshensky, who are faculty at NJIT and are part of our ITS Resource Center, and our students, Abul Fazl and Tufan, they are in the audience. This is a project that actually I presented 2 years ago an early exploratory phase where we kind of tested the 2-channel LiDAR to detect pedestrians on a sidewalk and alert drivers using connected vehicle technology on imminent crossing activity in front of them. And so that was kind of interesting because we realized that these alerts for drivers were effective in terms of reducing the oncoming speed of the vehicles. So we took this further down by essentially trying to equip intersections or actually mid-block crossings where you don't have really the traffic signals with some kind of alert system that will inform the drivers of the pedestrian traffic. And this is really an issue at mid-block crossings, because if they are not equipped with any kind of signaling technology, the drivers really need to visually see the pedestrians as they're about to cross, and then stop for the pedestrians. So many times you will see, maybe as a driver, you will kind of notice pedestrians too late, and then you're really in trouble. Should they stop? Should they start braking? Should they just go through it? Because pedestrian is not probably going to step on the roadway before they're certain that the vehicles will stop. So the solution for these kind of problems and issues and these kind of safety hazards, there are some. Most of them are to improve the visibility of the crossing, visibility of the pedestrians, and the one that most often is used are these rectangular rapid flashing beacons, which I'm hoping you all seen before. And essentially they are activated by pedestrians using pedestrian buttons. They would activate the beacon, which will start flashing, and then the oncoming traffic, the drivers will be alerted that there is a pedestrian on the crossing or about to cross, and hopefully they reduce their speed, they come to a full stop and let the pedestrians cross safely. This technology actually has been proven to be quite effective. And some statistics show from the recent studies that the driver response and adherence to the rules of the road to stop for pedestrians is up 90% in some of the locations that you would use rectangular rapid flashing beacons. And then pedestrian crashes are significantly reduced as a result of that, 69%. But one thing that is really required for this system to work, or to work properly, is for pedestrians to actually push the button. If they come to a cross and they start crossing without pushing the button, then the whole system is almost like a furniture on the roadway that doesn't really have any purpose. And what we actually we noticed this, anecdotally, all of us noticed this, have been noticing this for a long time. But what we kind of try to do is like, okay, let's see how much of a problem, how big of a problem this is. So what we did something, maybe I can't say it's really scientific study, but we did something as close as we could to the scientific study. We have a system like this right in front of our building at NJIT. It's a mid-block crossing that connects campus to a dorm. So there is a huge pedestrian traffic on this crosswalk. We have rapid flashing actually not rectangular, just a rapid flashing beacon with two signs that are flashing, and they are operated by a push button that pedestrians have to push. So I'm gonna play a video, 15 minutes, and we are counting here. We are counting pedestrians who are crossing and those who are pushing the button. Okay, so bear with me. Okay, so we got one, and then and you can just notice how much pedestrian traffic there is. So already you can see the problem, right? There are individuals crossing, there are groups crossing, there are those who cross that really not much traffic is coming through, but then there are situations where there is quite a bit of traffic coming through. So if you pay attention, you'll also see what maybe we can call it jaywalking. So people crossing outside of the crossing, right? That's right there, but I guess it's too far, like the one just crossed, right? So all of these are issues, right? So there's the number one issue is obviously, so look, 58 pedestrians were counted crossing the crossing, and only 6 push the button, 10%, about 10%, right? So 90% of the time, this flashing beacon is really not effective because it's almost like it's not there. So we actually followed up with all the students, and I really need to thank our students, Abu Fazl and Tufan. They were really very proactive and kind of recruiting the students for this survey right on the spot. And we asked them questions about using this technology, using the push button to activate the rapid flashing beacons. And some of the answers just kind of emphasize the problem. Number one, we asked them how often they use this crosswalk, and most of them use it daily because they're mostly students who either live on campus and they live in that dorm, or they kind of go to the dorm to meet with colleagues to study. And so it's a large number of them are on that sidewalk every day, and sometimes many times a day. So we asked them, why are you not pushing the button? And you know, most of them, the reason was either they were in a hurry, you can see here, so they were rushing to get somewhere. And then they also, some of them thought that, you know, they look left, right, and they feel like either there's no traffic or the traffic is so slow, they'll see me and they'll stop. And most of the time that's okay, that's fine, but there will be a situation if this becomes a habit when they're not going to be able to actually size up the situation properly, and that will cause or may cause crashes and issues. So there are other reasons, like they forgot, I don't know how, you know, doesn't make a difference. So that's those who think that, you know, it doesn't really matter if I do push or not, you know, drivers are not going to really change their behavior, something like that. I don't know. We didn't really go into details, but these are the answers. But I think the most important ones are these two reasons, right? Which means that highly likely then that's part of their habit, and it's not something that will change even if we kind of try to educate them more. That's our kind of conclusion. So we also asked them if they jaywalk. Some of them do. You know, why do they do it? And then again, you can see they're in a hurry. So most of the problem is that people are in a hurry to cross that crosswalk. And that's causing them not to pay attention or not to really, you know, push the button that really is there for their safety. Then sometimes the crosswalk was out of the way, and especially the guys who were crossing like in the sidewalks like 10 feet away, and that was too far. So, but again, that was one of the reasons they would jaywalk, that the crossing is not close enough. Anyway, but so all of these things really led us to think about how can this problem be addressed. And what we thought is that really, if that push button was pushed every time, then the system would probably be much more effective. And if the button is not pushed, and the reason we have the button is to activate the rapid flashing beacon, then can we activate that rapid flashing beacon by passively detecting pedestrians, not really expecting them or making them or you know, having them push the button, but somehow detect that they're there and just activate the rapid flashing beacon. So what we came up with is a system that uses, in this case, LiDAR. You could use other detection technology like cameras. So we use LiDAR to detect pedestrians as they are approaching the pedestrian crossing, and then when our system confirms that they are about to cross, we activate the rapid flashing beacon automatically without the need to push the button. The system consists of several components. One, obviously LiDAR up front, up on the slide. Then we have a computer that really has the intelligence. We developed a machine learning based algorithm that will collect the data from the LiDAR, and then will process that data to detect pedestrians, other objects, and also position of those objects on the road. So there is some computation that's required, and for that we need a computer. And then we use controllers. This is Arduino and Raspberry Pi. These are just small boards that really control the signaling between the computer and the rapid flashing beacon. Signaling meaning, you know, when the signal should be activated, deactivated, how long that activation should be, that kind of stuff. So the key advantage obviously is that, you know, we no longer need pedestrians to do anything. They just need to come to the crosswalk and start crossing, and the beacon will start flashing. So the concept is that, you know, this LiDAR would be positioned somewhere near the crossing, and it will be kind of monitoring this area. Obviously, it monitors the whole area in the site, but we can create these virtual zones, detection zones, where we can actually use the LiDAR to detect movement on, first of all, detect all the objects, then movement of those objects. We can recognize what kind of objects those are, and then based on that intelligence, we can activate the flashing beacon when it's appropriate to do so. This is kind of live kind of, I guess, visualization of the LiDAR data. So you can see that obviously it continuously has the continuous feed of points that reflect the objects, stationary objects like buildings, trees, traffic lights, anything like that, sidewalks. But then you will see pedestrians are also crossing their, you know, so essentially what this is showing is that, yes, the LiDAR can see everything. All of these points reflect objects on the road, but we can kind of train the model that we have algorithm that is processing the data to identify objects that are pedestrians. That's what we are looking for. We really want to identify pedestrians, and we also want to activate their detection when they enter these zones that we use for detection and the control of the rapid flashing beacon. So we set up this system that I just kind of described at the same crossing at NJIT, and the algorithm was developed by our students and Professor Lee, and it was implemented with some additional, keep saying intelligence, but I mean some additional rules that will also determine how long that flashing should occur. We also had a logic that was developed to identify groups of pedestrians crossing, so that you don't have to, like, every time you detect a pedestrian, you activate the beacon. If they are in a group, you only activate it once, assuming that the group will be crossing, not like 5 activations for 5 people who are together, something like that. So that's also part of the control algorithm. So this is how it works. So you can see now the pedestrian that didn't really press the button, but the beacon was activated as that pedestrian approached the intersection, right, automatically. The next example is that you can see now that, okay, so these guys were, some of them were crossing outside. We were able to actually detect the jaywalking and also activate the flashing beacon with, you know, by detecting pedestrians who are outside, crossing outside the crossing. The next group of pedestrians, so now this essentially will only activate once, and we'll watch the entire group crossing. When the entire group cross, then the activation will be terminated. A jaywalker will show up, some, just watch. And now see the activated beacon. Wow, they were like really far, but we got them. So again, that's the it's, I don't say a beauty of this system, but like really one advantage is that we can play with that length of that activation zone and kind of you know, detect pedestrians that are even outside of the crosswalk, but you know, keeping them safe that way while they're crossing. So we kind of, our conclusions are that this is really an effective technology that can be used to address these issues that I identified early on with push buttons and these crossings with rectangular rapid flashing beacons. There are some concerns about the cost of technology, some maybe concerns about the reliability of the technology, not in terms of how reliable it is in detecting the pedestrians, but maybe maintenance, ability to operate in adverse weather conditions and things like that. We've tested different types of LiDAR so far. We didn't really notice any issues, but we're looking forward to testing some of the some of these technologies this winter at NJT, and then we'll kind of continue to collect data and refine detection algorithms, because we do notice from, in some, over time that there are some false detections or missed pedestrians under specific circumstances. So the model is as good as our training for that machine learning model. So we'll continue to improve that. And then also the urban setting, like for example, if the crossing is in between the parked vehicles, so if you have on-street parking, that will kind of create some additional complexity of the system. If you have trees, you've got some other what we call obstacles or obstacles to the vision for the LiDAR, that would also create might create some issues that will have to be addressed with the algorithm. And then ultimately, we would like to find a way to, besides activating flashing beacons, we can stream this information to connect through connected vehicle applications to the vehicles themselves. So instead of, like if you are in a vehicle that's equipped with this connected vehicle technology, you can get an alert of the pedestrians crossing in front of you right on your dashboard, on your infotainment system. Even if the flashing beacon is not there, it's not installed, there is no really anything, right? There's no technology there for the pedestrians to even push, even if they wanted. We can create a system that can virtually send these messages to oncoming traffic as the vehicles are approaching the intersection. So imagine that there is no flashing beacon, pedestrians are crossing and vehicles are coming, but if you install a LiDAR or camera and any detection system, you can passively detect the pedestrians as they're about to cross, and you can send in real time the messages to the oncoming vehicles, which you can identify by geofencing, let's say, an area close to that crossing. So it's doable. We already tried it. It works in our lab. We just need to figure out now how to do it in real life, maybe at this intersection or this crossing at NJIT. So that's what we are planning to do next. So hopefully we'll be able to report more next time we see you. So I guess questions, no?
Yeah, thank you, Bronislav. I think we do have some time for some questions.
Yes.
Did you study the pedestrian crossings after you put the LiDAR in? Did people stop try to attempt to use the push buttons? In other words, they got accustomed to the LiDAR activating and the buttons were still present.
Well, we just did a small study and quite recently. This system was only installed for a short period of time. So I don't think any of our colleagues, students are actually aware that that system was there. We didn't tell anyone. We were just kind of activating it. It wasn't like, oh, no, you don't have to push and you don't have to do anything. We didn't post any sign or anything like that. It was really, I was saying incognito, but we did this like just to test the technology and see how effective it is. Down the road, if this is installed, we definitely want to. That's why I said the study we did wasn't quite scientific, although we did use statistics and we did proper surveying methods, but we need more data, and we'll need to design the experiment, like you said, to see whether the behavior of pedestrians would change with this, right? But 90% of them are not pushing the button anyways, even if they know that it's there. So,
hey, no, that's a great idea. I'm just thinking about the activation zone, because obviously you'll have people that are just going along the sidewalk and not making that turn. So I imagine once they make that turn to cross is when it gets activated.
Right.
Does that give enough vehicles enough time to I mean, a person will see a vehicle probably if they're close, but does that give vehicles enough time to stop?
Right. So the push button would activate the flashing beacon when you are there. So you are already, if you think about the system, the concept, right? You need to get to the crosswalk and then push the button. So the amount of time that the vehicle will have to see it is the same amount of time that it will take for our system to detect the pedestrian as it's approaching, or he or she is approaching the curb. So now just not pushing the button, we activate the flashing beacon. But the first question about detecting the, which pedestrians should really activate the flashing beacon, that's that machine learning code that, we have to we actually have to teach the system. We need to teach the algorithm which pedestrians are supposed to activate the system, and this really has to do with their trajectory. So if we can teach the algorithm to monitor the trajectories of the pedestrians, and then when they come to a curb, then activate the flashing beacon. If they continue walking past, they're not gonna activate it. And that's, again, machine learning is a good tool to kind of train the algorithm to kind of detect those kinds of trajectory patterns. Yeah.
Just a small question from my end. So when you guys tested, most of the testing scenarios we are seeing is in the daylight scenarios. Did you test for the nighttime conditions?
No,
Not
we
yet,
didn't,
right?
but we will. And I mentioned adverse weather conditions is another thing that we want to do. Most of that is not going to affect. We are hoping it's not going to affect much LiDAR detection, because LiDAR is not affected by the light. Camera would have a problem in nighttime if you are in a poorly lit location. This location probably wouldn't have that issue. LiDAR may have an issue with weather conditions. For example, snow. If it's heavy snow, big snowdrop, then that can obscure the LiDAR. We haven't seen that yet as a problem for this kind of application, but we'll test it. So we'll see. These are, by the way, 120. Well, we tested with 32 channel LiDAR, but now most of them are really being replaced by 128 channel LiDARs. Those are much more robust, and the sensitivity is much better. So you probably will not see, we're hoping we won't see that issue with them as well. Yes.
There's a similar issue of lack of use of beg buttons at signalized intersections. Do you see this as an applicable tool for getting time signals or like triggered signal changes at
Absolutely.
phasing?
Yes, same way. In that case though, we would also count pedestrians. So pedestrians will be detected, but also we'll be able to count them, and we would be able to put some weight on pedestrians at the intersection, and then come up with a logic to optimize signal timing to reduce the wait time of the pedestrians. And so the number of pedestrians will have effect as well, not just detection of pedestrians' presence. Right.
Thank you. Any other questions? We have time for one more.
I think one time you mentioned, like few minutes ago, when they cross the crosswalk, nearby the curb leaving, they detect it, right?
Yes.
Detect LiDAR.
Jaywalkers.
But how about if they're leaving, but they are also crossing the curb line? So how they know? Because once you finish crossing, you are also crossing the curb line. Let's say you are going from left to right. When you reach the right, how the detector know they are already crossing and not flashing again?
Oh yeah. So the trajectory. So
Right.
it's looking at the direction.
Right.
So that's why I said we not just detect pedestrians. The system also tracks their trajectory. So the trajectory is essentially crossing the line, some of those detection lines, and the logic is inherited to the, not inherited, it was developed and integrated into the system that the directionality of that trajectory will also determine when to not just start the activation, but also deactivate the flashing beacon. Like few seconds after the pedestrian leaves the detection zone, we will deactivate the
Thank you.
beacon. Yep. All right, so we'll save some time for additional introduction. My colleague, Dr. Beshensky, wasn't able to attend today either, so I will cover for him as well. And again, I'd like to recognize the team that worked on this project, include Dr. Beshensky, Dr. Joang Lee, our student Tufan, and Dr. Spasovic, who is in the back monitoring the room. So I see some issues with the font. Okay, we'll figure it out. So this project is is also related to safety, traffic safety, and this one deals with the detection of incidents. So one of the critical elements of effective traffic incident management is timely, accurate, and reliable detection of traffic incidents. essentially, the sooner we detect the traffic incident, the sooner the transportation agency, the operators will be able to size up the impact of that incident and, if necessary, deploy resources to manage traffic and mitigate any congestion or adverse impacts of that incident onto the traffic. Traditionally, incidents are detected using either some kind of roadside equipment like cameras, roadside detectors, and essentially those would tell us when the speed drops or suddenly drops, and then that kind of indicates some congestion. Or cameras will be used by the traffic operators in traffic operation centers to monitor traffic at different locations, and obviously when they see visually detect incident, then they will know that something is happening. Another way to detect, quote unquote, is to get reports from law enforcement from the scene of the incident. They will call traffic operation center and report an accident, incident and severity of that incident. The problem in all of the above is the number one, coverage. So we don't have cameras everywhere. We don't have, even on freeways that are well, I guess, covered by cameras. They're not close by. Sometimes you would have 10 miles or more between two cameras. So anything that happens in between, really no visual awareness. Detectors also, they can detect that something is happening, speed is dropping, there is a slowdown, but you don't really know why. So you really need someone to tell you, or you need to go and see what's going on. And then the first responders, they're not always there. New Jersey DOT has a really great service called Safety Service Patrol, but they only patrol busy interstate highways, and they are really effective in detecting incidents and responding, and in real time helping out motorists. But again, limited coverage. They are not on all the roadways, not even all the major roadways in New Jersey. When I say that, all freeway sections and multi-lane highways. And then law enforcement will sometimes call central dispatch unit or traffic operation centers, and sometimes they won't, because sometimes they're just busy attending the incident, right? And they really don't have time to talk to DOT and to report incidents. So there is a need to have a some alternative tool to detect incidents in real time or close to the time as they occur. One of such, I guess, new tool is crowdsourced data, and crowdsourced data is coming from the drivers, from the traveling public. And so we are expecting, or we are kind of looking for a way to leverage the reports about traffic conditions by the traveling public, and use that information to kind of as an information for us to detect incidents. And I'll talk about ways that we used in this particular study to try to kind of leverage that information to improve the detection of incidents. One of the main problems with crowdsourced data is reliability, and most of it obviously is reported by people like us. Some of us, actually, I see people in the audience who are trained for traffic incident management, and they're really professionals in responding to traffic incidents, and not just responding, but also managing and identifying them. But majority of the traveling public is not trained, right? So people will drive and they will see something, and they will look like, oh, there is a crash, there is an incident. They will be reporting that if, let's say, they use Waze or something similar. But it doesn't mean that necessarily it was the correct call or the correct assessment. So number one, validity, and number two, reliability. Some of us will be 100% accurate, and 100% of time will be, reporting valid reports, and some, will just randomly report, but sometimes those reports end up being not really valid. They thought there was a crash, but it wasn't a crash. Maybe it was a traffic stop. Maybe it was just a slowdown because of the volume. They don't know. But they just assumed, okay, there's something happening, maybe a crash, let me report the crash. So that's a problem, because when we get these alerts and we just use them as, oh, there is a report from Waze or, crash, and if we take it for granted on its face value, we'll be getting too many alerts, and majority of them will end up being false. And then what happens is your confidence goes down. So the next one that comes, you're going to say, oh, you know what, this probably is not even, worth looking at, right? So that's a problem when you have a source of information that is not trustworthy. So again, we looked at this study as a way to augment the existing detection methods. I mentioned cameras, I mentioned traffic detection, I mentioned connected vehicle data, and augment that with this additional source, which would be crowdsourced traffic data, in this case from Waze. The main advantage of crowdsourced information is that is for the traffic operation agencies cheap, almost no cost, right? We can just subscribe to Waze feed as their partner, and Waze kind of really likes working with state DOTs and traffic operations agencies, and they will kind of share the data with us or with traffic operations center. So really low cost of employing that. And we don't have to invest into human resources to monitor cameras. The more cameras we put, it's great. We got more cameras on the road. We can see, more of our network. But then you need to hire people to actually watch these cameras, right? Now we have another technology that will kind of use video analytics to detect incidents, but that also is not 100% accurate. So with Waze and crowdsourced data, that cost is not really there. So we can actually improve our efficiency at very low cost. Again, the main problem is how do we ensure that the validity of the reports is sufficient and their accuracy is sufficient, that we can integrate that as a valid incident reporting tool in our toolbox. So for those of you, I just assumed that everyone knows about Waze, but for those of you who don't, it really started as a navigation app, and then it kind of morphed into, but it was always crowdsourced, so that not just giving you directions how to get from A to B, it was also using the data from the users who were reporting various incidents, accidents, events, traffic stops. My colleague put police traps. So there is more to it than just the spot. But also getting there without being caught speeding, things like that. Anyway, I shouldn't be saying that. But one of the advantages is that now these drivers are becoming our sort of collaborators in managing traffic through Waze, right? Because they are sharing their assessment of traffic conditions. And so again, the problem is that how much we should trust their judgment and how much we should trust their reports. And you will see some of them are very trustworthy, some are not. And the problem is, we don't know who they are, we don't know their names, we don't know anything. They're all anonymous. So we have to figure out a way to kind of grab those reports that we think we should trust more and kind of ignore those that we don't think we should trust, right? And so that will reduce the number of false reports that we will just be wasting our time reviewing and paying attention to, and we kind of focus on those that are valid, that are trustworthy, that we should really take into account and kind of react to those as part of our incident management process. To do that, we developed two models that we integrated into one. Number one, we developed a what we called data filtering algorithm using this density-based spatial clustering of applications algorithm. It's just a machine learning method that processes large amount of data and tries to cluster them. And each cluster will be labeled like, okay, this is false, this is positive, right? So it's kind of, we're trying to look at all the ways reports that are coming in, and we are trying to use the information about those reports, and you'll see in a few slides the attributes that we use to cluster them. And we kind of create this cluster and say, okay, so if this report is in this cluster, it's likely to be valid. But if it's in this cluster, then it's not valid. We should just ignore it. And so that's kind of the gist of this machine learning algorithm that we used. And then we also wanted to see, well, if that's the first step, obviously, but the second step is, can we figure out which properties or which features of those reports are more influential in terms of validity of the reports. So, for example, if we get a report from a very trustworthy Wazer or Waze user, we can say, well, that's a factor that will really help us determine whether this report is accurate or not, right? And then there are other properties or features of those reports, I'll show you in a minute, that we can actually evaluate their significance in terms of the validity of the report. And to do that, what we did, our student Tufan was working on this, developed binary logic model to actually explore the statistical, I guess the statistical significance of each of those features of the Waze reports. So I guess I don't have my watch, but I can actually, okay, I'll try to speed up. So here we are just showing the data. So this is all the Waze reports over the course of the analysis period, which was kind of scattered across 3 years, 2021, 2022, 2023. This is the data that we obtained from Waze. So that's not just Waze reports that you would get on your phone or your app. Actually, it's the data that you need to subscribe to get from Waze as a database as opposed to alerts. So we were kind of, we worked with them and we kind of were able to get these in these kind of clusters. And so what we did, we kind of looked at those reports and we tried to match those reports to actual crash reports from NJTR1 reports. So these are New Jersey police crash reports that are collected by the law enforcement every time they respond to traffic crash. So what the idea was, okay, let's look at all the Waze reports that we got from Waze and then match those reports to those NJTR1 reports, right? And so what we were looking for matching, right? And we knew that not all the Waze reports will actually be valid. So that process actually gave us the matching between the Waze reports and crashes. So that's how we were able to label the Waze reports as valid and not valid. Those that we matched to NJTR1 reports were valid, and those that were not matched to NJTR1 reports were not valid, because obviously at the time and location the Waze report was submitted for a crash, there was no crash. So therefore, that was not a valid report. Okay, so that was the process of matching, and we used that process and the data that was labeled in such a way to train that DB-scan method to cluster the reports from Waze. How did we cluster? We clustered using various attributes of those reports. Each one of those reports, and this is not something you can see in the Waze app. That's why you need Waze to work with you, or you to work with Waze. The database they shared includes not just report, location, and time. It includes some additional information about the crash and on those who reported the crash. So we can see the reliability and confidence score, which is actually related to the user of Waze. So Waze, when you start using it, they track your behavior. They track what you report, when you report, and then they also track how other Waze users respond to that. So if you report a crash and then a bunch of Waze users confirm, yes, there was a crash, then your confidence goes up because now somebody validated your crash report, right? And so and Waze is tracking that. So the more thumbs up kind of thing you have, the more reliable you are as a user and as a reporter of crashes. Then we also looked at road type, crash type. They only have 3 types: minor, major, and nothing, no subtype. Type of day, which is either weekday or weekend, and then time periods. So what we kind of thought that maybe time periods were also going to be significant because maybe the reporting and the quality of reporting in different time periods would vary. So that can help also determine the validity of the reports. And then there are report ratings based on the type of user. So this is what Waze actually did. They used all this information, and then Waze has their own algorithm that will give us the reporting rating. Level 1 means new user. We can really verify. And then there are levels 2 to 5, which are, they call editors. Those are the ones that actually are more experienced and more reliable users. And then there is level 6, which is like, let's call it super user. Like this is like someone we should definitely trust, you know, without asking any questions. They call them Waze champions. Those are the ones who actually help them, you know, develop the application and inform their development better. Okay, so that's Waze. We also use NJDOT Tier 1 crash reports. Hopefully you all know about that, so I'm not going to dwell on this too much, but we really focused on location, time and date and severity of the crash. That's what helped us to identify whether Waze report actually was matching a crash, a real crash. So as I said, Waze reports, they're very, it's a huge database. They come in, you know, at very high frequency, and obviously there could be multiple reports for the same event. So like we did some kind of mapping, I don't know if you can see, but there are a lot of events that have the same color. It's all one event. Actually, it's only one crash, but you can get like a few dozen reports for the single event, and they will not happen at the same location, right? Because I'll be driving and I see something that looks like, okay, it's a queue, it's a congestion, and I see something probably looks like a crash, I'm going to report the crash. And somebody will pass it and report the same thing, right? So we are reporting the same crash at different locations. So we have to actually filter all that as well and kind of match it to the same event to be able to kind of train our model to detect valid reports. So that's what happened in the step where we localized each crash based on NJDOT 1 report. We localized a segment of the roadway that we were looking for anyways reports occurring there, or, you know, coming in at those locations. So we kind of focused on a 0.5 mile, half a mile section around the reported location in Tier 1, NJDOT 1. And then we also look at the time, because obviously that reporting coming in you know, at various points within the duration of the incident. But another thing is that we are all aware that NJDOT 1 is not super accurate at the time when the time of the crash report. Like, so the time of the crash in the NJDOT 1 is not necessarily accurate. You know, I'm not saying it's not, you know, we shouldn't look at it, but it's not accurate in, like, if you say this crash happened at 10:15. Well, it may not be happened. That may not be accurate. Maybe it happened 15-20 minutes earlier. Maybe it happened 15-20 minutes later. Maybe it did happen at 10:15. You know, so it really depends on the law enforcement, the officer who was putting together the report, because obviously most of the time the police officer was not there when the crash occurred, so they had to collect that information from those who were in the crash. So that is a little bit kind of, I don't say subjective, but almost subjective. So we kind of take that, and we can't really assume that's the only time we should be looking at. So we created this 1 hour kind of window around that reported crash time to identify any Waze reports about the crash, about that crash. So essentially it's a temporal and spatial buffer, if you will, that we use to identify Waze reports that correspond to a crash. And that's, again, for the purpose of labeling. So this is just some statistic about the matching that we obtained. So, for example, out of about 120,000 records of Waze reports, we were able to match about 10%, about 19,000, 15. Well, it says 50. Actually, no, 15.6%. So this is the matching rate. right? So this is actually how the percentage of Waze reports that were actually valid, right? That we could validate they occurred at the crash locations, at the reported crash locations, and the rest of them we just couldn't validate that they were actually related to an actual crash. And then you can see through the years, the 2021 data set, like portion of the 2021 that we evaluated had a relatively higher matching rate, and then 22 and 23 quite close to each other. In terms of type of crashes, obviously major crashes. So major, minor, that's subjective. Like, I don't know, I guess people who use Waze, they will just see the crash and then they will say, okay, it's major or minor, depending on if they see a lot of damage on the vehicles, and then they say, okay, major if it's something like a fender bender, minor, something like that, right? So it's not necessarily matching the crash severity rating that, let's say, DOT and law enforcement uses, but you can see that actually the ratio of major 26.3% is not really, probably it's not the ratio of actual number of major crashes of the total crashes, but probably people, drivers, Wazers, let's call them Wazers, Waze users, will respond more to more severe crashes, right? So if they see something minor, they're not going to even push the button, especially if the traffic is not affected. But major crashes will probably affect traffic much more, and then they will be, I don't say obliged, but they will be kind of, they will feel like, let me inform everyone, let me push the button and inform. So that's why we get a more, better coverage of these major events or major crashes by the users of Waze. And then some of the matching analysis of the type of roadway. We see that freeways, 27% of all matched reports are on freeways, 49% on primary streets, which is majority of the roadway lane miles in New Jersey, and then secondary street and other roadways. Okay, let me skip through. I'll talk about this in a minute. So, and one thing that we also notice is very indicative is that, remember that rating of the Wazers, of the users. So you can see that the number of reports with high rating is very low. So these, I don't know if you can see, but 10, 9, 8, 7, these are the user ratings. So you can essentially the number of reports that are coming from the users who are rated high is very low. This line are those who are rated, number one. So these are new users, maybe not so reliable reports, right? So the majority of the reports are from those users. And then as their rating, as their reliability, so to speak, right, goes up, meaning they're growing in confidence, the number of those actually in the data set is lower. Okay. What we did, that kind of covered the first part where we kind of try to filter between or to filter out the non-valid reports and just keep the valid reports. The second part is this understanding of the different attributes of these crashes. As I mentioned, type of crash, type of day, time of day, type of user, type of the report, and we try to see which one of those factors was most significant. So we found that, and I apologize, you can see here, but this is the type of day. Is it a weekday or weekend? That's a significant factor. So it's 11.1% more likely that the report will be valid if this is on a weekday. So weekends are less reliable reports. Then you have time of day, peak periods. In just conclusion, peak periods were more likely to generate, or valid reports are more likely to be generated during peak periods. Freeways and primary streets or primary arterials, again, high likelihood of valid crash reports. And then obviously the higher the reporting rating, the higher the chance of valid report. And then crash types, major crashes are actually much more likely to result in a valid report. So, and that's what the conclusions are exactly that, right? This is what we call, and actually that's a good news. Why is that the good news? Is that because peak hours on primary streets, that's where a crash would cause the most problem for traffic. And that's when, those are the types of events and locations and times of day when DOT will need to do something to respond to those crashes, right? Outside of those times in different locations, maybe crashes will not, it won't be so critical to have a really fast response. Peak periods, a lot of traffic, a lot of congestion, that's when the crash will create the most impact. And if we can get reports during those times that are highly reliable, validated, or verified, then we can actually really improve the response if we augment our current reporting with these waste reports, right? So that's a good news from the study we did, looking at the attributes and their significance. And then I already mentioned the impact of other crashes. I just want to kind of get to a closure here in the interest of time. But anyway, so we do have some more work to do with this. Number one, we probably want to expand the data set and then explore some of the additional features like seasonality. And then we also look at these additional variables, weather conditions I mentioned. We didn't really look at that, but maybe reporting crashes in certain weather conditions is going to be different. I mean, the validity of those reports. And then we want to see how this these machine learning algorithms can be introduced to integrate dynamic changes of the ratings of these reporters or wasers, so that we can actually use their feedback continuously and what you call dynamically change the rating, and that will help us kind of filter out those valid reports in the future. So that's it. Hopefully, I know I'm over time, but
Thank you, Bronislav. Thank you again for sharing your research and the work you and your colleagues at NJDOT are doing. Round of applause. So I want to make sure we have enough time for our final session. So I would say any questions, do feel free to reach out to Bronislav or someone on staff today, and we'll put you in contact. But let me invite Rukaya Alferis and Greg Woltman up to the podium for our final session, and I will introduce them. Rukaya Alferis is a PhD student in the Department of Civil and Environmental Engineering at Rowan University. She is working as a research assistant at the Center for Research and Education in Advanced Transportation Engineering Systems, and she has been working on several projects to address transportation safety issues and maintain equity across transportation systems. Rukaya has been selected as a recipient of many awards, and she has several published papers in prestigious journals and conference proceedings. And Greg Woltman is a research project coordinator at the Alan M. Voorhees Transportation Center at Rutgers University. His work with the New Jersey Bicycle and Pedestrian Resource Center includes research focused on micromobility, safety, pedestrian access for older adults, best practices in pedestrian scale lighting, and federal zero deaths initiatives and grant programs. As a staff researcher at the New Jersey Department of Transportation's Bicycle and Pedestrian Resource Center, Greg dedicates his effort to researching and synthesizing information on different federal discretionary grants, the Safe System approach, and the FHWA's proven safety countermeasures to expand New Jersey's active transportation networks and enhance safety for vulnerable road users. So, thank you.
Now, is it working? Okay, cool. Okay, so as he mentioned, my name is Greg Waltman. I'm here with my research partner, Rukaya. Whoa, bad font. Anyway, this work is being done through this with funding support from the New Jersey Department of Transportation, which is federal highway funding. I am from the New Jersey Department of Transportation's Bicycle and Pedestrian Resource Center, and Rukaya is with CREATES, which is the Center for Awesome backronym. I love that. This project is also in partnership with the EDC7, the Everyday Counts initiative, which this year, in year 7 of the initiative, there is a topic which is a nighttime visibility for safety, which is where we fit in. Our project team is myself, Rukaya, and then our directors or managing directors, Leanne Von Hagen and Dr. Mohammed Jalayar, who could not be here because they both have other things that they are doing today. So we're going to talk about background of our study, the scope, design considerations and criteria that we have kind of identified through our results, takeaways, and what this means for safety in New Jersey. Okay, so just to start with some examples. This we took the actually Leanne took this picture in South Brownbrook, New Jersey, from her windshield. She was in the passenger seat, just for the record. And you can see that we have a pedestrian, but there's actually just a very wide variability in their visibility based on a lot of things. Currently over here, oh, I can point. Can I point? Oh, yeah. Over here, we have pedestrian scale lighting that is just like off, and it's actually making it making the visibility of the pedestrian and the amount of time it takes to identify them increase. The visibility is lower, and the amount of time it takes to react to them increases. We see them over here just a few seconds later, much more visible, much quicker much quicker identification. We see it again here. We have a pedestrian here and here. Can we really see them right away? No, there is actually lighting directly above them. However, this is road scale. This is not pedestrian scale, and it does not actually provide much benefit to the pedestrian. As you can see, the sidewalk over here is much brighter because there's actually pedestrian scale lighting as a de facto from this bodega. So we're and then this parked car is our third like key factor that we're going to just like talk about what we already know about lighting and pedestrians. First of all, pedestrian crossing the street is generally not always the easiest thing to do because of yielding and stopping behaviors. Road lighting, especially when it comes to road scale or vehicle scale lighting, does not necessarily serve pedestrians. This one here, and being one of those. Illegal parking is a compounding factor to poor visibility, and that visibility can change by the foot. We also, from other research out of the Blaustein School and from the Voorhees Transportation Center, we have identified some hotspot. There was a hotspot analysis for bike ped crashes, and as we can see in the left, this is all bike ped crashes in the state. And where there's blue, there's an underrepresentation of crashes, and where it's red, there is an overrepresentation of bike ped crashes. And what we can see is that there's a high concentration in North Jersey in the densest, most walkable parts of the state, as well as in Atlantic City and Cape May. However, if we look at it from a fatal perspective, where are those crashes fatal, there is still some up in North Jersey, but we see it mostly in Camden and in South Jersey. And what we have here is a discrepancy. One factor is a discrepancy in the amount of lighting, especially out here in Vineland and in the South Jersey region. A lot of these are high-risk rural roads, and they do not have any lighting, much less pedestrian scale. Lighting is a proven safety countermeasure. In New Jersey, crashes are 6.5 to 7 times more likely to occur in dark conditions, and are this is for pedestrians and bicycles and pedestrians. 6.5 to 7 times more likely in dark conditions, and 2 times more likely, twice as likely, if there's no lighting at all. And we've identified there are a few key areas for improvement where we can really kind of allocate our resources because they are major trip generations for pedestrians, vulnerable road users, and that includes school zones, transit stops, busy intersections and corridors, and marked crosswalks, which are mid-block, which kind of ties into our last couple presentations. Also, VTC has done some additional work that kind of built up to this. We have this 2007 report out of the VTC, a pedestrian lighting in New Jersey. Shout out to Raji, who wrote that 15 years ago. And also we have as a resource out of the Bicycle and Pedestrian Advisory Council, which is an NJDOT sponsored BPRC activity. We have this primer that was produced for pedestrian scale lighting, which provides some details about sighting, spacing, and different considerations. However, it is pretty detail and instruction light. It is pretty high level. Okay, and this is where Rukai starts.
Thank you, Greg. And here we start with the scope of the study, that how we started building this guide that can help engineers or municipalities to determine what and how to provide an let's say a decent or enough amount of lighting for pedestrians to provide them safe and comfort on the roadways. So after we defined the research problem, we looked into multiple guides and resources that is already in there. Some of them published from the Illuminating Engineering Society, AASHTO, and CHRB. Some of them are published also by FHWA. From these, we did synthesize our findings into the design considerations and criteria, which I'm gonna explain in details. Starting with the lighting system design considerations, overall, whenever we're talking about lighting on roadways, there are three aspects that are being considered, starting from safety and comfort for all road users without overlooking pedestrians and bicyclists, which are the vulnerable road users. Environmental impact, considering the new, for instance, lighting that are being installed on the roadways, such as LEDs, and their impact on environment, the wildlife, and even the human health. Energy consumption, how much energy can we save by using the best option or the most energy efficient option for the lighting on the roadways. Starting with the design selection criteria considerations, there are two ways or two types of criteria that we need to consider whenever we start determining the lighting that we need in a roadway. The primary selection criteria and the secondary selection criteria. The primary one, technically or primarily look into the levels of lighting that we need to provide in a roadway, and that's illuminating and illuminating, which I'm gonna explain in a bit. The secondary criteria, which focuses and guide on the characteristics, the selection, and maybe the feature itself for the lighting system that we're putting on the roadway. The primary criteria, which covers the luminance and illuminance. So let's at first differentiate between the luminance and illuminance. If we have a lighting source, such as what we see in the slide in here, the amount of light that falls from that light source on the ground itself, this yellow circle in there, it is what we call illuminance. And this is usually measured by lux or foot candle, and how much we have from this illuminance, or the more we have illuminance, the more coverage we have for the lighting. It has three types. It comes horizontal, vertical, and semi-cylindrical. I'm gonna expand on these in a bit. But we have also luminance in our primary criteria. The luminance is how much light we have reflected on the eye, or it measures the brightness of an object that is being observed from a specific direction, how bright that object is. For instance, for that pedestrians that we see in there, how much visible it is for the eye direction that we see on the other side. And for the luminance, it's measured by candela per square meter. And for like the basic knowledge, if we have higher luminance, for sure we have sooner and easier detection for the object we're trying to see. And in our case here, it could be a pedestrian, it could be a bicyclist. To split out the three types or the three measures of the illuminance, we have the horizontal, vertical, and semi-cylindrical. The difference for the horizontal illuminance, it is the amount of light that falls on a flat surface, horizontal surface, and the wider that plane is, the more visibility we have. Once we look at the vertical one, it is the amount of light that falls on the vertical plane, and it's measured or recorded based on the eye level of the observer. When we look at the semi-cylindrical, the picture itself says it, but it considers more the 3-dimensional aspect of an object, which is mostly needed whenever we're talking about pedestrian scale lighting or the enough visibility for bicyclists as well. Each of these has additions or tweaks that we need to add once we are determining the final illuminance and luminance that we need for efficient lighting in a specific roadway in a specific neighborhood that has specific characteristics. But those all are split out in diagrams that I'm going to present at the end, but the basic knowledge about them, to differentiate them, we need to present them in here. Coming to the secondary criteria that we have there's multiple aspects of the lighting that we need to consider in the secondary criteria. First one of them is the corrected color temperature of a light source. And this is technically the color output of a light source. It is measured by the degrees Kelvins. It ranges from 100 degree Kelvin to 10,000 degree Kelvins from warm to cool. The less it is, the warmer the light is, the higher it is, the more blue tone of a color it would take, and the cooler it becomes. Now, once we're talking about the pedestrian scale lightings or even street lightings themselves, they do not usually go beyond 6,000 degree Kelvins. We do not see that blue tone of color on the roadways. Once we reach the usual that we have is up to 6,000 Kelvins. Now, the 5,000 degree Kelvins is the natural or the neutral white of a color that we have, and the high pressure sodium lights that we have nowadays, some of them range between 1900 to 2000 degree Kelvins, which is right in here. So it is warm. Now, there is this dilemma or this conversation between one more thing. So for the LED lighting, it goes more towards the neutral white and the blue tone of color, but it does not usually exceed the 6,000 Kelvins whenever we're using it in the roadways. Main reason is the conflict between the visibility that we need and the human health. Higher Kelvins means some effect on the wildlife, on the human health, on the sleep quality for people. So we need to find the balance between this, between the resources that we have reviewed. The ideal number that was found is 3,000 degree Kelvins, somewhere between enough visibility for roadways and at the same time enough health for people or no disturbance for people's health. Second item of the secondary criteria is the surround ratio. The surround ratio is technically the amount of light that is spilled over the roadway that is being lit. The way how we measure this is by counting the amount of foot that is being lit on after the roadway or on the shoulder in addition to the sidewalk, divided by the amount of light that is lighting one lane of a roadway. The optimal ratio for the surround ratio for the pedestrian scale lighting is 80%. And it is 80% because we need more coverage on the shoulder of the sidewalk to provide enough visibility for the pedestrians. Now, if we are counting this or defining the optimal ratio for surround ratio for roadways, this optimal ratio would decrease because we would look for saving lights and not having spillovers on the rounds. But here we are looking for pedestrian scale lighting, so we are looking for some more lights on the shoulders in order to provide visibility for pedestrians and bicyclists. Third item is glare. Glare is any discomfort or difficulty combined with lighting once we directly look at the light. And technically, glare becomes more problematic whenever we have lights that is at 16 foot or shoulder or shorter, which is the pedestrian scale lighting height or mounting height. And with glare, we can fix this problem whenever we're talking about the pedestrian scale lightings by increasing the semi-cylindrical illuminance, which can fix this discomfort that is associated with the glare. Light trespass, it's the amount of light that we has, and it's lighting something that should not be lit, either going on the sky, or it's going into the priority line for some buildings or neighborhoods for people. If we look at the picture on the side, we see how glare is it this? No, I want to go back. The up one, right? It's fine. So glare is right, this one that is hitting onto the person's eye. Everything beyond the area being illuminated is a spill light, and it's hitting the residents, it's hitting the property line. It's not what we really need to illuminate. Technically, illuminating any item that we don't really need to illuminate. The lighting type selection and considerations. So we have 5 types of the lighting types. It's classified based on the distribution of the light from type 1, 2, 3, 5, 4, and 5. Whenever we're talking about the pedestrian scale lighting, the optimal or the best to use is from type 3, 4, or 5. And the main reason of this, because with pedestrian scale lighting, we need the light to go more than linear. If we look at type 1 and 2, they are more linear distribution of the light. However, for 3, 4, and 5, it goes more horizontal with some curving with the light distribution than it's being purely linear. So it can provide enough illuminance and light needs for pedestrians and bicyclists. Type 5 is more the circular coverage of a light, and this is usually used either in intersections or in places that are open areas for pedestrians. So whenever we're talking about the pedestrian considerations design, after looking at the main criteria, luminance, some of the secondary criteria, we need to consider what type of facility we're trying to illuminate. There are 3 main types for pedestrians. Either we're talking about crosswalks, could be mid-block or intersections, adjacent to roadways, and that could include the sidewalks or the walkways. We have the purely walk trails for pedestrians, which is separated from traffic, and this is not our main considerations in this study because we're trying to look at the areas where there is a conflict between a vehicle and a pedestrian. In addition to looking at the pedestrian facility that we're trying to eliminate, we need to look at the pedestrian volume in the area. There are 3 levels of the pedestrian volume, from low, medium to high. Low, if we have 10 pedestrians per hour or less. Medium, it's between 11 to 100 pedestrians per hour. And lastly, high, it's wherever we have more than 100 pedestrians per hour. Now, because we know that bid count is very rare to have, it's expensive to collect, there are some along way let's say land uses or typologies for the areas that can help people to guide the way how they can provide lighting. So whenever we're talking about low pedestrian volume, it's more could be the suburban streets with single family dwellings, or low density residential developments could be also the rural or semi-rural areas. Whenever we're talking about the medium areas, it's the downtown office areas, libraries, apartments, parks, industrial areas, and the near transit lights. High pedestrian areas, it's mostly downtowns, crowded areas, stadiums, theaters, and transit terminals. This can guide whenever the bid count is not available for people or for the engineers who are trying to work on the pedestrian scale lighting. Coming to the outcome that we got from this study. So after reviewing and inventorying the guides that we have on hand, defining the criteria, we came to our design decision trees that defines the thresholds or the ways to provide sufficient lighting for pedestrians. There are 3 main items that are provided within these decision trees: the illuminance and luminance, which is the lighting levels, the placement for these lightings, which are mounting and spacing, and lastly, the lighting fixture. if we start with the first decision tree, oh no, it's fine. So it's basically considers the lighting level, how much illuminance and luminance we need to provide for specific area, either if we're talking about intersection or adjacent roadway. So the flow chart, it just walks you through it. We start from the question or the node if we are in an area that is adjacent to roadway or not. If yes, we continue with the flow chart. Is that a crosswalk or not? If it is a crosswalk, we end up with 20 vertical loops as an optimal illuminance. If it's not, we need to understand the pedestrian volume level. We go to the options, either if it's a low or medium or a high. If it's low or medium, we have 20 vertical loops as optimal illuminance. And similar, if we go to the high, we have 10 semi-cylindrical loops as optimal illuminance. Then we try to figure out if it's a rural or urban areas, and from that we determine the optimal luminance. Now, one important thing that I need to highlight here, if you see the +2 cylindrical, semi-cylindrical loops on this side, from this side, and from down here, you see the +0.5 candlefoot per square meter, and similar here. So all these additions, it's the additions that we need to consider for the glare problem. So we said whenever we have pedestrian scale lighting that is have the height of 16 foot, we will have glare problem. By adding those luminance and luminance frequency fractions, we can fix the glare problem in these areas. So with that, the engineer could determine how much illuminance and illuminance we need for the area or for that specific facility that we're trying to illuminating. But still, we don't know how much height we need and how much spacing we need to put these lighting on. For the placement, we consider two things, mounting and spacing. Mounting, usually between all the resources that we have went through, it ranges between 15 to 18 feet of a height. Once we're talking about spacing, it differs. If we are in a downtown area, we're good with 40 feet between each of the lights. If we are not in a downtown area, we go to a roadway adjacent area. If it's an intersection, we go with minimum 10 feet between crosswalks and approaching vehicle, and that's to give the setback for the pedestrian. If it is adjacent to roadway, we need to look at the width of that roadway. Now it becomes the roadway width becomes a problematic. One last chart. If it's more than 50 feet of a width, we need to place it with 50 feet separate with opposite to each other, the lighting. If it's less, 60 feet with alternating pattern would be enough. Last chart, it just tells us about the lighting fixture. Now one important thing that I need to tell about this, lighting fixtures are usually depending on the vendors that are contracting with the municipality that's providing the lighting. This is just a guide. If we have historical areas, we need to consider the historical type of a light. If we are doing a standard, the standard of each Department of Transportation is usually determined. The watt and the type of a light is usually we do from 3 to 5 type, and the wattage ranges between, depending on the area we're providing the lighting at. But this is just for the information, because mostly the lighting fixtures depends on the municipality and their vendors and the cost and the budget that is being allocated. This is the before last slide. I'm gonna back to Greg.
All right, very quickly, just the key takeaways. We developed this, and this was a research task because we had been hearing from municipalities that this is like an information like black hole. Especially in like small towns, there's really not enough local knowledge of lighting. It's very complicated. There's a lot of factors. So we've developed these like flow charts, as Rakaya went through, to really to determine and help them on a planning scale and some preliminary ideas where to place. The document will also kind of discuss how to work with utilities and what that process looks like in New Jersey, because that does change depending on what square foot of the state you're in, it seems. And the best practices for LED conversion, because this is also something that works towards our sustainability goals and also through as part of the BPU push to kind of recalibrate our lighting towards LEDs. Additionally, lighting is an equity issue for both roadway and public safety, and there has been a disproportionate investment in lighting in underserved communities. So that should be considered, especially if we're talking about scoping or where we're putting additional lighting and investing those resources. As one more thing for sustainability, this is kind of an approach to sustainability as it does allow for better safety and comfort of pedestrians, meaning that people can shift later at night into into walking in more environments and at more times. And I don't even remember what the last one is, so we'll just move on.
Last one, it just says whenever we're designing the roadway of the lighting, it has to be in cooperation with other departments within the municipality, because there's the right-of-way for pedestrians, there's other furnitures on the sidewalk, there's the landscapes that all has to be coordinated together to make the best use out of the sometimes very minimal space that we have for this. That's it. Thank you for being here. Any questions?
For more information, if you would like to scan and find out more about any of our centers that we work with and out of.
All right. Thank you, Greg and Rakaya, for your presentation. And I want to say thank you all for joining our safety session. And thank you to all of our presenters as well. So now we are at the end of the research showcase. So thanks for joining us and have a good afternoon, everyone.